It's the classic meme. One water bucket and it's all over. One block of TNT and it's all over. All it takes is one bucket of water. But what if there was a redstone build that could actually survive a water bucket? One that could survive a blast of TNT? The other day, I was watching a Veritasium video on QR codes, and there was something in it that kinda blew my mind. If you take any QR code and mess some of it up or destroy it, there's a chance it'll still work fine. And that got me thinking, what if I used redstone to make a QR code? Would it still work if you blew up some of the screen? So I set out to do just that. I wanted to make a machine where you could type in some text, press a button, and have it generate the QR code. So if you typed in a link, the QR code would literally take you to that link. This is the story of how I made a QR code generator with just redstone. I hope you enjoy. Step 1 of any project is to do research, so I started by learning as much as I can about QR codes online. And I gotta be honest, I was kinda disappointed with the information out there. I mean, there's a Wikipedia article, and it does a pretty good job explaining QR codes, but not on a super detailed level. I needed the nitty-gritty. I needed to know exactly what every single bit in the QR code meant in order to generate one myself. Eventually, I found the actual QR code specification, which had the details I needed, but it was locked behind a paywall. So as a last-ditch effort, I went to see if anyone else has made this in Redstone before. That way I could message them to see what they did. Which took me to this video by David Jr., who made his own super nice QR code generator. In the description, he credited a website called Thonky's QR Tutorial. And let me tell you, finding this website was an absolute game changer. It's like the holy bible of QR code generation. It has all the details and a bunch of tools and tables to help you along the way. And while I was at it, I still messaged David just to get as much info as I could. He was nice enough to have a pretty long call with me, so big thank you to David for all your help. As I read through the Holy Bible, the first thing I had to decide was what kind of QR code I wanted to make. QR codes have 40 different sizes, called versions. Version 1 is 21 by 21 pixels, all the way up to 40, which is 177 by 177. QR codes also have 4 different levels of error correction. The lowest level, L, can recover about 7% of data, medium can recover 15%, quartile 25%, and high 30%. And finally, QR codes have 4 different modes, depending on what kind of data you want to store. Numeric mode for just numbers, alphanumeric for numbers and uppercase letters, byte mode for any character in this character set, and kanji mode for any character in this character set, a set for Japanese characters. Now, the amount of data a QR code can store depends on all 3 of these. I found a really nice table on the website that shows exactly how many characters you can store depending on these 3 factors. And that led me to decide, kind of arbitrarily, to use version 3, error correction level L, and byte mode. Well, actually, byte mode was not arbitrary. I wanted the user to be able to type in text, like a link, which has more than just letters and numbers. And I'd prefer it to be in English, so byte mode was the only option. But yeah, these settings meant my QR code could store up to 53 characters, which felt like plenty. A YouTube link, for example, is only 43. Now that the type of QR code was decided, I started building in Minecraft. I didn't really know what I was doing yet, but I at least knew enough to start making the screen. Version 3 is 29 by 29, so I made a simple 29 by 29 screen out of 2 by 2 pixels. This allowed me to turn on any pixel I want with a signal in the back. Then I continued to read through the tutorial, and I learned about all the constant parts of a QR code. Every QR code, no matter what kind, has these 3 squares in the corners, called the finder patterns. They basically just tell the scanner, hey, there's a QR code here. And there are always white separators as well to make sure they're easily readable. Some QR codes also have 1 or more smaller squares called the alignment patterns. These help the scanner rescale or reshape the image depending on the orientation it was taken from. The version I chose, version 3, has exactly 1 alignment pattern. Next, there are the timing patterns, which are these zebra stripes near the top and left. These help the scanner determine the size of the pixels. Then there's the dark pixel, which is literally just a pixel that is always dark. And finally, these spaces are reserved for a 15-bit format string, duplicated to be in 2 different areas. And those are all the constant patterns. The rest of the QR code is for the data bits and the error correction bits, which are not constant. They're going to change depending on what data you want to store. Back in Minecraft, I went ahead and put in these constant patterns. In a QR code, white is 0 and dark is 1. So I started by inverting the entire screen with torches. That way the screen was 0 by default, and I could power a pixel to make it 1. From there, I just drew all the patterns by placing redstone blocks to power them. I also made a simple texture pack to make lamps black and white because I felt like it looked much better. Plus, it made it a lot easier to scan. It's still possible to scan without a texture pack, you can try this one yourself, so the texture pack is not necessary. It just makes it look better and scan better. Next, I started working on the keyboard. When it comes to Minecraft keyboards, there are a lot of different options, but I decided to just stick with what I know best and make a classic button keyboard. Then I had to figure out which characters the keyboard should have. Since I chose byte mode, each character will eventually be encoded as 1 byte, or 8 bits, which means there are 256 possible characters. But if you look at the character set that byte mode uses, only 191 of them are actually printable characters, and about half of those are special characters or characters not used in English. So I decided to only include these characters on the keyboard. I put them into a QWERTY layout, and I made 2 shift keys with levers as well. Then I used an encoder to make each key output its 8-bit code. For example, when you type lowercase e, it outputs this, the code for lowercase e. Or if you type uppercase h, it outputs this. And if you really want to type a character that isn't on the keyboard, you still can. Over here, you can enter an 8-bit code manually and press this button to type it. Now I needed some kind of display to actually see what I was typing. Typically when I make text displays, I just make my own custom font, like in my last project video. But since there were a ton of characters this time, I decided to follow this font I found online, created by KK. It's 3x5 pixels per character, which is pretty much the smallest you can go before it gets painful to read, and it had everything I needed. Special characters, lowercase letters, even things like curly brackets. So then I put all these characters into a ROM, or a read-only memory. When you put in the 8-bit code here, it uses a decoder to access that character and output the pixels to the display. If you put in this code, for example, you get the exclamation point. Or if you put in this code, you get capital P. Then I duplicated this display and built a shift register to shift the characters as you type. For example, if you type Matt, then the M gets put here, then typing A will shift the M over and put A on the right, typing T will shift those over and put T on the right, and so on. It just keeps shifting over, allowing you to fill up the whole display. Now, since I knew my QR code could hold 53 characters, you would think I'd make this 53 characters wide, but I actually made it 43. I think I just thought that as long as it can hold a YouTube link, it's fine. Then I put this whole thing above the screen and I hooked up the keyboard to it. And now I could type anything I want and see it up top. With that, the easiest parts of this build were out of the way. Every constant part of the QR code was filled out and I could type any message on the screen. So I went back to the tutorial and finished reading about how to fill in the rest of the QR code. Like I said earlier, the entire rest of the QR code is for the data bits and the error correction bits. Let's focus on the data bits first. There are 440 data bits, or 55 bytes. These 55 bytes are essentially one long binary string, stored in a snaking pattern. But let's just visualize this string normally, from left to right. The first 4 bits are for the mode. Since I'm using byte mode, it's just 0100. The next 8 bits are for the character count. If you want to send the message ABC, for example, that's 3 characters, so this would be 00000011, or 3 in binary. Then just fill out the characters byte by byte. Sticking with the ABC example, you would add the byte for A, add the byte for B, and add the byte for C. Next, add 4 zeros. This just aligns it so that it's back on a byte. And then the rest of the data string, all the way out to 55 bytes, should be filled with this repeating pattern. And that's it. That's the data string. In other types of QR codes, there are more rules for the data string than just this, so if you're making your own QR code generator, don't just use this video. Make sure to read through the tutorial like I did, and double check that it's actually correct for your type. As another example, let's encode Matt Batwings. The mode is still the same. The character count is 12 this time. Here are the 12 bytes for MATTBATWINGS. Here are the 4 zeros, and here's the repeating pattern. By the way, this is why you can only store 53 characters, because if you take out the mode, character count, and 4 zeros, there are 53 out of 55 bytes left over. Now that I knew how to structure the data string, I got to work making it in Minecraft. This part of the project actually went really well. These are all the concepts that went into it. Starting with the 4-bit mode, well, this is just constant, so I didn't actually need to build anything. For the character count, I used a binary counter. It starts at 0, and the idea is that when the user presses a key, it counts up by 1. So as you type A, B, C, it counts up to 3. Then for the characters themselves, I used a register to store them as they came in. As you type A, B, C, for example, you can see that the 8-bit codes get stored. And then the 4 zeros are constant again, so no work there. And finally, for the repeating pattern, I used this. At first, the plan was to have the redstone repeatedly add the pattern to the end, just like you would do by hand. But then I realized that that's overkill, and there's a cool trick you can do instead. Notice that when the number of characters is even, you always get this pattern, meaning it stays in the same physical place when you have 2, 4, 6, or any even number of characters. And if the number of characters is odd, you get this pattern. This stays in the same place when you have 1, 3, 5, etc. So I basically just hard-coded both of these cases, and I made the evenness of the character count decide which one to use. If it's even, it looks like this, or if it's odd, it looks like this. This trick made it much faster, and I was proud of myself for coming up with it. And that's pretty much it. All of these concepts work together to create the data string. Once they were all built, I connected them together and hooked them up to the real build. I spent an entire day debugging, which is way more than I thought I'd have to. Honestly, if I took more time testing them before rushing to connect them all, it probably wouldn't have taken that long, but oh well, I got it all working. And now, after I typed a message, I could press this button to create the data string. Let's go ahead and type in A, B, C, and create. And we got this. If you read it from right to left, you can see it's correct. All that was left to do for the data string was put it on the screen. To do this, the tutorial says to start on the bottom right and place the data upwards following this zigzag pattern. Once you get to the top, move over to the next column and go downwards. Do this for the entire data string. And if you run into a pattern that's already there, just skip over it. So in Minecraft, I decided to do this by using one redstone line to physically follow the pattern and another redstone line to lock it into place. For example, if you send in a single bit, you can see it follows the zigzag pattern. And when I flip this lever, it locks into place. So the idea is that if you send in a stream of data, the entire stream will follow the zigzag and get placed when you lock it. And of course, you can make one that goes down as well. Once that was working, I scaled it up to the entire QR code, making sure it skips over all the constant patterns. If you send in a single bit, you can see it traverses the entire QR code. However, you might have noticed it's traversing backwards. Why is that? Well, if you start to send in the data string, let's say the first 4 bits, 0100, and then lock it into place, it's unfortunately not correct. Placing 0100 should actually look like this. To fix this, you can either reverse the data before sending it in, or you can reverse the traversal. I chose the second option, so that's why it looks like it's traveling backwards. But anyways, now I just had to attach this to the screen and send in the data. Once it's in the correct spot, I made it automatically stop. Beautiful. Welcome to the hardest part of any QR code generator, error correction. These error correction bits are the secret sauce that allows a scanner to still read it if it gets damaged. Going into this project, I knew that generating these bits was going to be difficult, but I didn't realize just how difficult until I started reading through the tutorial. Apparently, you have to do a polynomial division, which I've never done with redstone before. In fact, I didn't even remember how to do that on paper. But thanks to more tips from David, I got my confidence back and I started designing some prototypes on my notebook. Before I go any further though, let's talk about how error correction works in the first place. Let's say I want to send you a message that is the 4 numbers 1576. If there's an error in transmission, you won't be able to tell what happened. So instead of just sending 1576, I'll also send 2 more numbers, A and B. These 2 numbers will help you check if there were any errors. Now imagine these 6 numbers as the coefficients of a degree 5 polynomial. I'm going to set A and B so that this can also be written as a degree 3 polynomial times x minus 1, x minus 2. That way, if you plug in 1 or 2 and evaluate it, you should get 0. If you don't get 0, you know there was an error in transmission. By the way, the x minus 1, x minus 2 is called the generator polynomial. And I didn't have to pick 1 and 2, these could have been any numbers. Thus, there are lots of different choices for a generator. So now, I need to find the values of A and B. If I divide the message without A and B by the generator, then I get a degree 3 polynomial, which is what I want, plus a remainder. And if I move the remainder to the other side, I now have the exact setup I want. A degree 5 polynomial with my message that equals a degree 3 polynomial times x minus 1, x minus 2. Therefore, A is negative 173 and B is 154. So now I go ahead and send this message. You receive this message, and if you get 0 when you evaluate it at 1 and 2, you know the message was sent correctly. But what if there was an error? Let's say the third digit, 7, gets corrupted and becomes an 8. Now if you evaluate it at 1 and 2, it's not 0 anymore. To figure out where the error occurred, one at a time, you can set each coefficient to a variable. Then find the value of that variable, setting the polynomial to 0 at x equals 1 and x equals 2. If you get two different values, that digit was sent successfully. But if you get the same value, that digit was not sent successfully, and it should be equal to the value you got instead. In this example, the value you get at the third digit is the same. It's 7, so you know the third digit was originally a 7. This is called Reed-Solomon error correction, and it's what a QR code uses for these bits. Okay, but how does it use it for those bits? Well, remember how there are 55 bytes in the data string? Those 55 bytes are like the 1576. They're the numbers you want to send. And then instead of adding 2 more numbers for error correction, A and B, it adds 15, A through O, if you want to think of it that way. Altogether, that makes 70 total coefficients, which can be thought of as a 69-degree polynomial. Nice. Then to figure out what A through O actually are, you divide by the generator again. But now, the generator isn't x minus 1, x minus 2, it's this. I'm honestly not sure why it's this, I'm just following the tutorial. Let's call it g of x. After the division, you get a polynomial and a remainder, just like before. Moving the remainder to the other side tells you exactly what A through O should be. But this is actually going further than you need to. If you just leave the remainder as is, then these 15 coefficients are the error correction bits that the QR code needs. Just convert each one to 8 bits, and fill up the rest of the QR code following the same zigzag pattern. One problem with this though is that after the division, the coefficients of the remainder might become larger than 255, which can't be represented with 8 bits anymore. So to solve this, the tutorial says to perform all computation in something called Galois Field 256. I'm not going to get into the details of Galois Fields in this video, but the basic idea is that in this field, you only work with numbers 0 to 255, or 8-bit numbers. Any computation you do must stay inside this range at all times, which is called closure. Instead of doing addition and subtraction the normal way, which might create numbers outside the 8-bit range, addition and subtraction become bitwise XOR. For example, 3 plus 5, or 011 plus 101, is 6, 110. It probably seems weird to call this addition, and it's probably even weirder to say that subtraction is the same thing, but honestly, the reasoning behind it is not super important. The more important thing to understand is that using bitwise XOR for addition and subtraction satisfies closure. 8 bits XORed with another 8 bits will never produce something outside of 8 bits. And then multiplication is even weirder. To multiply, you basically do 3 things. Convert both numbers to new numbers, which I'll refer to as alpha numbers, using a lookup table. Add the 2 alpha numbers using regular addition, applying mod 255 to the result, and then convert the alpha number back to a normal number using a lookup table again. Obviously, this is a very brief summary, and I recommend reading through this section in the tutorial if you're curious about why it works. Again, the main point is that this also satisfies closure. This version of multiplication will never land outside of 8 bits. But what about division? Isn't that what this whole thing is about? Well, yes, but it's a polynomial division, and the algorithm to do that only requires addition, subtraction, and multiplication. So as long as you can do those 3 things, you're good. You might think that after reading all this, especially all the Galois Fields stuff, that I would have been feeling really overwhelmed. And I mean, I was for a little bit, but only until I realized that working in a Galois field is a huge advantage for redstone. For example, to make an adder or subtractor, you can just stack a bunch of XOR gates on top of each other. So that's what I did. If you put in 101 XOR 011, you get 110. Then to make a multiplier, I just followed the 3 steps. The 2 numbers get converted to their alpha numbers using lookup tables, the alpha numbers get added together using real addition plus mod 255, and then it converts back to a normal number using a final lookup table. For example, according to an online simulator, 100 times 25 should be 109. So if I input 100 and 25, the output is 109. And now I had all the tools I needed to do polynomial division with redstone. But that didn't mean it was easy. I spent a ton of time drawing layouts on paper, calling with David again, and just really trying to rack my brain to design the best circuit for this. And after a day or 2, this was the final design. It might not look like much, but that's only because I found a lot of simplifications during the process. Then I spent another day or 2 building it with redstone. And I swear, I must have gotten unlucky or something, because I kept running into the stupidest bugs ever. For example, did you guys know that this circuit unlocks a repeater, but this one doesn't? I have no idea why. They have the same timings, but it's true. Stupid bugs like this took me hours to find. But I bore through the pain because I knew it was going to be really cool when it was done. And eventually, I had this, a polynomial divider. The top polynomial, or the 55 bytes from the data string, go in here, and the bottom polynomial, or the generator, is kinda hard to see, but it's these redstone blocks along here. I was able to use redstone blocks for the generator because for my QR type, it's constant. So let's run an example. Let's say you want to send the message subscribe. The data string looks like this, so I'll put that into here. Then I'll speed up the game and press this button. After about a minute, I get the correct remainder, which means these are the error correction bits. From here, the rest of the build was pretty much smooth sailing. I hooked up the polynomial divider, and I made a circuit to send the remainder to the screen, filling up the rest of the QR code. But there was one more thing I had to make in order for the QR code to work. You see, after the data and error correction bits are placed, the QR code might end up having big blocky regions, which are more difficult for a scanner to decode. So a mask is applied to try to break these regions up. There are 8 different masks, each with a different set of locations to invert. Note that masks are only applied to the data and error correction bits. Nothing else should be affected. So which mask should be used? Well, according to the tutorial, you should use the mask that best breaks up blocky areas, thus giving the scanner the best possible chance of working. To do that, apply all 8 masks and evaluate each one using an algorithm to find something called the penalty score. The mask with the lowest score is the one that should be used. But in reality, you don't have to do this. Technically, you can just pick any mask. It might not have the best chance of scanning, but any mask you pick will still create a perfectly valid QR code. So since this evaluation process didn't sound very fun, I just decided to always use mask 0. And in Redstone, building this mask was really easy. I just put some torches in a checkerboard pattern behind the screen. And with that, the QR code generator was done. All the nights debugging, all the problem solving, it was over. This might sound really sad, but I got kind of emotional at this point. This was a project that, even a year ago, I would have been too scared to try. After all, polynomial division and Galois Fields are not the easiest things to understand. But I proved to myself that I can learn new things and design new circuits from the ground up. So I hope this inspires at least some of you to go after things that might seem impossible. Because trust me, even though there's a lot of pain, there's also a lot of awesomeness. If you enjoyed this video, subscribe, and if you really enjoyed it, consider supporting me on Patreon. I hope you learned something, I hope you enjoyed. Peace out, guys.